Recording. So as we had seen in the last class that thermite welding, right? This is one type of welding wherein we are able to join large structures, right? Are able to fill gaps which are large, right? Wherein more metal has to be filled so that joint so that we can have the joint, right? And this is more popular for filling up, welding rails. Okay, rails as we have in railways, right? So to start with, thermite or thermite welding, right, is a type of fusion welding process, right? We are trying to fuse the two components. It is also known as exothermic welding or bonding because, as I said in the last class, we are trying to have an exothermic reaction, right? The heat is generated because of the exothermic reaction. So that is why this is also known as exothermic welding or bonding. This process is used for welding large and heavy structures, right? As I was talking about, wherein more amount of metal is to be filled, and especially where the places where you require, where there is no power available, right? Like electrical power is not available. So how do you convert? How do you generate heat? Is what the problem is that will face. So to overcome that problem, right, to go to remote locations and be able to generate that heat for welding, we are going for this thermite welding, and we'll see why this is preferred for remote locations. And another point is it requires no electrode and power supply, right? This is also another advantage that as unlike the other type of welding we have seen, wherein we have used a lot of electrodes, right? This one does not require an electrode and power supply also, as we have discussed. The principle is in this process, the welding is done by pouring superheated liquid steel around the parts that are to be joined, right? So we're trying to pour in superheated liquid steel, right? And the way that liquid steel is brought to that superheated state is because of the Untitled reaction. Okay, that is the first point to note. A short molding process is to be done before welding. We'll see that how that wax molding is done. So that mixture, as I was talking about, the exothermic reaction, right, is a mixture of fine aluminum powder and iron oxide, right? That produces a very high temperature on combustion used in welding and for incendiary bombs. So that is what responsible for this generation of heat, right? And therefore the high temperature. And if it involves aluminum, thermite reaction, if it involves aluminum, is also called as Goldsmith aluminothermic reaction. Usually this reaction is triggered by burning magnesium ribbon in presence of barium peroxide. So basically the ignition material is magnesium ribbon in the presence of barium peroxide. And as for the composition, you have by weight 75% of iron oxide and 25% of fine aluminum powder. That's the ratio. That's we can see in the next point also that we have a ratio of 1:3 by weight, right? We can also use copper or chromium instead of aluminum, right? Those are also possible. As for the working, you see the ends of part to be joined are kept parallel with a uniform gap between them. So, for example, two rails are to be joined. Those two rails will be kept side by side, right? We'll see in the next diagram that you have those two entities kept right beside one another, and there is a uniform gap maintained. Now that gap is filled with wax, which becomes the pattern, right? Now molding sand is wrapped around wax pattern, pouring gate, heating gate, and rises are cut. So basically, once that wax comes out, you have that gap remaining, and that gap will be filled with the molten metal, right? You see here, this is your crucible, wherein that superheated molten metal will flow in, right, through the strapping pin. And this setup, what you have prepared, is around this. This is to be welded. Okay, these are the sections to be welded, basically rails. we're looking at a cross section of it. So if the weld material is, if the weld is to be made around this section, then you have to pour the molding, have a mold right around this section. So you are trying to make these cavities so that the molten metal is given way to fill this, what do you call, space, and then the riser, just as we have in the casting, right? So we are trying to give it that the channels, all the channels that are required, as we have seen, starts from the pouring basin, runner, gate, riser, etc. And before that, you have this preheating gate, wherein using a torch, you are trying to preheat the setup, right? So that this molten metal, which is a very high temperature, if it enters here, there is temperature gradient, and that would lead to cracking, etc. of the base metal. So to avoid that, we are trying to preheat, right? With a preheating gate, we are trying to preheat the setup before the molten metal is poured in. Okay. You see, joints to be welded are preheated by a flame, which is an external source. And due to this preheat, the wax melts and goes out. So the first thing that happens is the wax melts and goes out. And the next thing is you are trying to bring that setup to a certain temperature so that there is not much temperature gradient, right? Because of that molten metal flowing in to the joint. Now, after the melting of wax, the weld joints are preheated due to flame, right? Then heating is stopped and the heating gate is closed. So that's where the heating gate is closed. And therefore, no other external source of heat can come in except the molten metal, right, from the top, as we have seen here. Okay. Now, as for the preparation of thermite, you see how that thermite is prepared, right? This is one aspect. That how do you prepare that mixture? So that mixture of aluminum iron oxide in the ratio as we have seen 1:3 is placed in a crucible, right? Barium peroxide is added to the crucible. Barium peroxide arises by the reversible reaction of O2, that is oxygen, with barium oxide, right? So when that barium oxide, it reacts with oxygen, you have barium peroxide. The peroxide forms around 500 degrees centigrade, and oxygen is released above 820 degrees centigrade, right? And the mixture is ignited using a matchstick or small magnesium wire. We'll see in that video hopefully that using that either a matchstick or you see here magnesium wire also to be able to ignite that mixture, you have to have some source. So that combustion takes place in the crucible, right? Due to combustion, thermite reaction becomes superheated liquid within maximum time of 30 seconds. So that's how quick that combustion is, right? That superheated liquid, which is pouring metal, have a temperature of around 2500 to 3000 degrees centigrade. If we are looking at Fahrenheit, you have 5000 degree Fahrenheit. The reduction of ferric oxide by aluminum is highly exothermic, right? And therefore the iron form will be in the molten state. So basically we're trying to have that iron, right? So that, and aluminum is chosen as metal since it has strong affinity towards oxygen and its oxide, right? So that we have, the Al2O3 as we have seen, right, earlier, and as was explained, highly exothermic compound, right? That's the reaction that is taking place. And aluminum is reacting with this ferric oxide, right? That heat, what we are getting, that heat is actually our byproduct, right? That is our intention here, right? That heat is responsible for melting the base metal. As for the joining process, you have the crucible placed directly above the joint to be welded, right? As we have seen in the diagram. After creating of joints, the liquid thermite steel from the crucible is poured into mold between the gap to weld. The molten metal solidifies and weld is completed, right? As we have discussed earlier. Once that crucible releases that liquid molten metal, it flows in to that cavity, right? We have created with a molding sand. And it solidifies over time, and then the weld is completed. You see here, this is your crucible, right? Tapping pin, so that this molten metal can come in, right? All through this setup as I was talking about, right? You see here, they have the heating gate and this molten metal channels also at the same side, on the right side. So that both the preheating is done from the right side and also the molten metal goes in through the right side, right? So that's what happens, and then it rises with the riser, right? So if that is the section is to be welded, you have to maintain some space, right? As we have seen that excess material that we have for the weld can be adjusted, right? It'll create a bump, isn't it? As for every kind of weld, you have some excess material that can be later grinded, etc. But you have to have that material, right? Extra material that comes off as a bump, right? So you see, as for the steps in making a thermite weld, you have these steps what we have discussed, right? You see, it will flow in and then form a gap. I'm sorry, fill that gap, right? Now the scheme of steel pouring into the mold after the thermite reaction. You see this, the cross section of that rail, right? So it fills in, right? As for applications used to weld very large works, as we have discussed earlier, joining of rails, one example, pipes, even broken teeth on large gears, for example, those dam gears, if you have seen, they're quite big, right? So if there are broken teeth on those large gears, how do you weld them? With the help of thermal welding. Large framework also, like big structures, right? Architectural structures. This process is generally used for welding ferrous metals, right? Even because the exothermic reaction that we have is able to achieve that temperature wherein the ferrous metal can be melted, right? So that comes off as a positive point. Advantages, as we have discussed, very large structures can be easily welded, which is not possible with other kind of welding, right? You require more time and more filler metal will be required. So here you are trying to compensate for that. No power supply and electrode needed, as we have discussed. So this is very much suitable for to be utilized in remote applications, remote areas wherein there is no power supply or very hard to get any electrode also that is to be carried. Disadvantages, skilled laborers are required here because it's a very tedious process. Manual, we can call it, it's not automated. So therefore skilled labor is required here. And there's a time consuming process, right? Very lengthy process. You have to prepare the mixture, you have to burn the mixture, you have to prepare the molten metal, and then you have to prepare this here at the weld site. You have to prepare all that setup, right? All that gating system of what do you call this, runner, gate, etc. And then once when the molten metal is done, you have to pour it and then wait for it to solidify and then remove all that excess uh, gates and runners, etc. Once the weld is done, right? So it's a time consuming process. Doubts so far? Okay. Now let us have this video so that we can understand this process.
I am free of diabetes and I have stopped taking all
often called in many names.
Able to hear the audio also? Okay.
Shielded metal arc welding is called stick welding, while gas tungsten inert gas welding is called TIG welding. Similarly, exothermic welding is called thermite welding. Thermite welding is a type of welding procedure which uses molten metal to join two thick bars of metal. Thermite welding is most commonly used in welding two separate rails in train tracks. Unlike most other processes of welding that we've discussed up until now, thermite welding does not use any electricity for welding. This makes it suitable for welding work at remote locations. The heat required for welding is mostly created by exothermic chemical reactions. The most commonly used exothermic reaction involves aluminum dust and oxides of any other metal. Aluminum dust reduces the oxide of another metal as pure aluminum is highly reactive. The most common reactant is rust, which is also called iron oxide. When this mixture is ignited with heat, the components undergo a redox reaction. The oxygen from iron oxide splits and joins pure aluminum to form aluminum oxide. During this process, huge amount of heat is generated. The pure iron melts due to the intense heat generated, and
You see, all of that is your excess, the gating system, and right, so that will be chipped off, right? So you can have that weld, right? The final
fills the gap provided in between the rails. As we mentioned, thermite welding is mostly used to weld railway tracks. One of the first railroads to identify and use thermite welding was the Delaware and Hudson Railroad of the United States in 1935. The weld quality of chemically pure thermite is low due to the low heat penetration into the joining metals. Another drawback of this is that pure iron is used to fuse two rails together as opposed to strong steel. To avoid yielding pure iron, a few pellets of high-carbon alloying steel are added into the thermite mixture. To get a proper railroad weld, the ends of the rails being welded are preheated with the help of a gas torch till they start to glow in orange color.
we have discussed gas welding, right? So that torch, which the torch of that gas welding is what you're seeing here. You see those two pipes, they are being connected to two gas cylinders. Acetylene, for example, if they're using acetylene and fuel gas, the other thing is oxygen. So those two pipes or hoses are combining to this torch, which is responsible for preheating, right? So gas welding comes in handy here for preheating. Okay.
This is done to ensure that the molten steel from the thermite cauldron is not chilled instantaneously on touching the cold rail tracks. The welding process is as follows. A gap in the rail track is identified. Two mold clamps are placed on either side of the rail, just above the gap in the rails. The entire mold is then sealed properly with packing sand to prevent leaking of the molten metal. Slag basins are provided on both the sides of the mold to collect excess metal and prevent overflow. The entire thing is then heated with the help of a gas torch to get them heated up. They are heated till they become red hot. A metal container or crucible is then placed over the mold. This container is filled with thermite. The entire mixture is then ignited, which causes a rapid exothermic reaction to occur. The heat causes molten metal to flow through the mold and settle down on the slag basin. Once the exothermic reaction in the crucible settles down, it is removed. The packing sand, slag basin, the mold, and the clamps are all removed. The main reason why this procedure is used in rail tracks is due to the remote location of rail tracks. The same welding work can be done with electro-slag welding too, but carrying all the bulky equipment around for long distances is not very feasible. Finding a suitable power source is also a hard thing. This is the reason why thermite welding is preferred in this case. Well, that's it for this video, guys. We'll meet again in the next one.
Right? Doubts from that video? Okay. You see, the next type of welding is TIG welding. Okay, the full form is tungsten inert gas welding. So there's this inert gas. We'll see why it comes off in the category of inert gas welding. Okay, tungsten inert gas welding. Tungsten because the electrode that we are using is made of tungsten, and inert gas is because we are trying to use inert gas for shielding the weld area, right? You see, also referred to as GTAW. What is GTAW? Gas shielded tungsten arc welding. Okay, this is also known by this name, and we will also call it with GTAW or TIG welding. Both are fine. So in TIG welding, a tungsten electrode heats the metal, and shielding gas, most typically argon, protects the weld from airborne contaminants, right? As we have discussed, the electrode that we are trying to use is made of tungsten because it can carry a large amount of temperature, right? It will not melt with lower temperatures. So it can bear high temperatures, and it is stable also. And shielding gas, right? Most typically argon, protects the weld from airborne contaminants, as we have seen. That's the role of the shielding gas. You see, TIG welding uses a non-consumable tungsten electrode, right? So that tungsten electrode is not being consumed, right? It is only responsible for generating the heat. Another filler material would be supplied, right? That is what will melt. The filler material will melt due to the heat generated by the tungsten electrode, right? So once that filler metal melts, it will settle down at the weld area, right? So that is what is responsible for creating the weld. So this is very important that we mention it is a non-consumable tungsten electrode because tungsten is not being consumed in the process. Filler metal, when required, is added by hand, as I said. Shielding gas protects the weld and tungsten, right? It protects the weld area. And also the tungsten, because when it is at a high temperature, it is bound to undergo oxidation, etc. So that is also avoided. As for the setup, you see, if this is your workpiece that is to be welded, okay, you have the TIG torch, right? Tungsten inert gas welding torch. This is connected to your power supply, right? And as we have discussed, other end of it, the welding return, right, is also connected to the workpiece. So you have positive and negative terminals. And so this power supply is what is responsible for increasing the temperature of the tungsten electrode, right? And so that arc is generated, right, because of the power source. And shielding gas supply, right, is done with the help of a cylinder, as we have discussed. Inert gas, it could be argon or helium, etc. And the main supply, of course, which is responsible for generating this power here, and therefore the current. You see a closer look up of TIG welding, what happens in TIG welding. So as you are going from, this is the direction of travel, from here to there. You see here, this weld area is already done. So what is happening is, this non-consumable tungsten electrode, right, is trying to, the passage of current, right, goes from here around to the base metal. So an arc is generated, you see here, arc is generated, right? The arc is very directed. It's not like as we have in arc welding, the general arc welding. The arc is directed, it is very directional, and here is your welding rod, right, which will melt and gets deposited here, right? And this gas nozzle, right, you have the shielding gas supplied here from here. Sometimes, and most of the time, it is supplied. I mean, it is an integral part of the welding torch. The shielding gas, what do you call it? Setup is integral with the torch, so that the shielding gas comes in, it tries to surround the tungsten electrode, right? And therefore, when it comes out, it also protects the weld area, right? And that's what there is, right? Current conductor, right? So that this tungsten electrode receives the current, right? That's what about TIG welding. As for the advantages, it welds more metals and metal alloys than any other processes, right? This is what do you call, quite a precise process, we can say, because of the generation of arc, which is directional and ability to achieve higher temperatures by being stable. Also, stability is also another reason, because of the shielding gas. There's no formation of oxide and other contaminants, so it is able to weld more metal and metal alloys than any other process. Okay, much variety that we can have metals and metal alloys. No sparks or splatter, right? There are no sparks, as I said, and therefore no spatter. Basically, the molten metal would not disperse here and there, right? No flux or slag. We are not using any flux. No slag is formed, right? No smoke or fumes, right? As for example, in arc welding, you will have a lot of fumes, but here, no such thing. And high quality and precision work. This is very much suited for creating precise welds, especially in the aerospace industry. TIG welding is more common, right? Because it is able to achieve higher quality weld, and that it is also precise in terms of dimensional control. It is also precise. Pinpoint control, right? As I said, you have more control over the weld, over the weld quality and the dimensions. You see here how neat the weld is here. Here as well, and this minute weld here also. That is, we have joined this bush to this main body. So how you do that is with this weld, which is very precise, as you can see. Unlike this bigger weld, this weld is very smaller. So ability to achieve that weld, having the